Thank you. I will present a paper that I published recently with Luciano Tubaro and Luigi Amedeo Bianchi, both from the University of Trento, about a problem in construction of Volterra processes and some possible relation with statistics. So this kind of problem was introduced 25 years ago, more or less, by Uhlenbeck, who proposed the analysis of an Ornstein-Uhlenbeck process of the kind stated in equation 1. So you have very simple Ornstein-Uhlenbeck. WT is a one-dimensional Wiener process, and let's say that we take initial condition equal to 0 for simplicity. And the point is to choose alpha k to be a sequence of independent identically distributed random variables which are independent of W. In order to keep the presentation simple and without loss of generality, we can assume that the sequence of alpha k is defined on a different probability space that I call omega bar with a sigma algebra f bar and a measure p bar. So as you see in equation 1, we have two sources of randomness, the alpha k, which is the coefficient in the Ornstein-Uhlenbeck problem, and the noise. What okay is we have an explicit form for xk, which is well known, and we consider the empirical means, so the partial sums of xk from 1 to n divided by n. What we can prove is that if we send n to infinity, and a certain condition on the coefficients alpha k that will remind in a moment, we have that the sequence yn converges to a process yt, and this process is a Volterra process, so it's Gaussian but no longer Markov, with a kernel that is described in terms of the coefficients of the alpha k. Okay, so in order to explain this last statement, I need to recall you that alpha k in the original paper by Uhlenbeck were gamma distribution with parameters mu and lambda. So mu is the shape parameter, and we will assume that mu is larger than 1/2, and the scale parameter lambda is positive. And so, as you see, both lambda and mu enters in the description of the kernel that defines the process yt. And this converges happens in the p almost surely, but so almost surely with respect to the measure p bar. So, as you can imagine, what you have is that the Brownian motion W is not affected by the operation of taking the partial sums because it's constant with respect to k. And what you are doing is to take an average with respect to the alpha k, which are instead exactly given in this space omega bar. And the convergence is quite strong because you can prove that this happens pointwise, so for any t, but also in a sense of trajectory, so in the space of continuous function for arbitrary intervals a, b. Okay, all of this is known, and what we were interested in was to see if we can extend in order to cover more general classes of kernels in the Volterra process. So here is a list of some other references, starting from the original paper, and then there is a couple of papers of Cyprian Tudor and Sedai and also Ingrid Hilbert. And in these papers, they changed the kind of noise. So instead of having a Wiener process, they choose fractional Brownian motion and also more general noises like Hermite processes and so on. And also there is some result about the choice of different kind of kernels. What we will do is to construct these average, so the empirical means processes, by choosing a different kind of kernel. And in order to do this, the simplest way to start, the simple point to start is to choose a Volterra process XT instead of the Ornstein-Uhlenbeck process given before. And in order to make this clear, we will propose the following equation. So this is a fractional integral equation, where xk is now described as the convolution between the noise, between the process xk itself and the fractional derivative kernel, the risk fractional derivative kernel g rho, where we assume that rho is larger than 1. Wt is again given Brownian motion. We will not change this. And also we will not change for the moment the sequence of alpha k. So alpha k will remain a sequence of IID gamma distributed random variable. So the difference here is that we introduce a new parameter, rho, and so we assume that we will find a different kind of kernel with respect to the kernel given by Iglo and Tardik. In order to proceed, we face the problem that we don't have any more a simple form of the solution with respect to the exponential kernel, but we need to introduce the Mittag-Leffler function. It is known that the Mittag-Leffler function is the kernel that generalizes the exponential function to the class of integral differential equation. And in our case, the Mittag-Leffler function can be expressed in terms of the scalar resolvent function, or rather, the scalar resolvent function as alpha can be defined in terms of the Mittag-Leffler function via the equality that says that S alpha is given by the Mittag-Leffler computed in minus alpha times TLR rho. And well, this is exactly an extension of the original paper, because if you take rho equal to 1, then it is known that the Mittag-Leffler function is the exponential function, and what you get is that S alpha is exactly the kernel that was seen in the previous formula about the Iglo-Tardik case. Now we write again the sequence of empirical mean processes, now with respect to our new, today's more general processes xk. And we want to show that the similar results that proved before holds in our case. What changes clearly is the form of the limit process. And this limit process will be given in terms of more complicated somehow function g, which depends on both parameters rho and mu, rho, mu, and lambda to be precise, but the dependence on lambda is very simple and can be taken inside, where this function is morally given by the expectation in the space omega bar of the random variables S alpha t, where alpha is a generic element of the sequence alpha k. So we need to give sense to these 3 steps. We need to define this function, prove that it is somehow reasonable, that we can use it in order to define a Volterra process, show the convergence of the sequence of empirical means to this process. And finally, what we are most interested in is to study the asymptotic behavior of these processes as t goes to infinity. Notice the following, and I want just to emphasize it, that once you take the empirical means of the yn, here in formula number 2, you still get as the limit a stochastic process, because these empirical means just cancel the dependence on the randomness given by the space omega bar, but they keep the randomness given in the space omega. So ynt is a stochastic process for fixed trajectory in omega bar, is still a stochastic process in omega. In order to proceed with our plane of work, we start with defining this function G rho mu. So this function is one kind of generalized Wright-Fox type function. It's one of the many functions with a name in the literature, and it's given as the ratio between the proclammer symbol mu k, the gamma, so the extension of the factorial function gamma in k rho plus 1, multiplied by zeta to the power k. So it's an extension of the Mittag-Leffler function, since the Mittag-Leffler function is equal, but with 1 and in the numerator of the ratio instead of the proclammer symbol. We can prove some properties of this function, and so assuming that rho is larger than 1, we prove that this function is an entire function in variable zeta in C, and the order of this function is 1 divided rho minus 1. So you see that rho larger than 1 is a necessary condition. Moreover, we can prove that this function behaves like the analog Mittag-Leffler function, so it is not positively defined, it oscillates among the 0, and it converges to 0 when on the positive semi-axis, when I send x to infinity, with an order of convergence that can be estimated explicitly. And this order is 1 over x plus 1 over x to the power mu. Remember that mu is the shape parameter in the, is the scale parameter in the gamma random variable alpha. So we just plot an example here to see the difference. Okay, so as I said, mu is the parameter that you find in this distribution. And one interesting computation that you can do that is important in the sequel is the following. The random you need to take the expectation negative power of alpha. So for positive powers of alpha, the expectation is very simple. It's given by 1 over lambda to the n times the mu to mu n, the proclammer symbol. But for negative values, so for negative exponents, the convergence, so the existence of the expectation, holds true if and only if mu is larger than 1 over 2 rho. So we will assume from now on that this condition holds. Notice that this condition is compatible, is an extension of the condition given by Gloet-Tardik, because remember that their paper required that mu should be larger than 1/2, but in their case, rho was equal to 1. So we have an extension, and notice that since rho is larger than 1, we can take a larger class of gamma distribution, or if you want, we can take mu in a larger set. And the relation, as I told you before, between the kernel and the alpha random variables is given in this lemma, which is just a question of computation. That is that the expected value in the space omega bar of the function S alpha of t, which is defined above in the slide. So it's the Mittag-Leffler function computed in the point minus alpha times t to the rho. And alpha is a gamma distribution with parameters mu and lambda. We have that this expectation is given by the function, Fox-Wright function g rho mu, computed in minus 1 over lambda t to the rho. And I will not give the proof of this. It's just a question of writing as alpha by means of the Mittag-Leffler function and somehow exchange the expectation and the series and then compute the expectation every term of alpha, so the powers of alpha. What is more interesting is to study the limit of the empirical mean processes. So let's define y and t in this way. Notice that, okay, in principle, I should write 1 over n times the series of the integrals. Then, since n is finite, this is a finite sum, and so I can take the sum inside. And as you see, the sum just goes to the just the index of the sum is k, and so only the S alpha k is involved. So I can apply the law of large numbers. Okay, I can suppose that I can apply the law of large numbers, in which case I have that this sequence converges exactly to the expected value. And so let's say if everything works fine as we can expect, what we have is that we can substitute the sum inside the integral with the expected value, and so say that the limit of yn is given by the process y, which is defined below. And this is exactly what happens, and so that's why I'm telling you this. So I have the convergence not only for any t, but I can prove the convergence also for in the subnorm for any time interval AB, and for simplicity, we will only do this in the time interval 0t. And this limit converges to 0 almost surely with respect to both randomness. Now, notice that yn t minus yt is an Ornstein-Uhlenbeck process, or if you want, is a Gaussian process with that is the integral of a function going to 0 almost surely with respect to a linear process. So we can see that also that the limit is 0 also in the first probability space, so also with respect to p. And the proof of this theorem is sketched in these few lines, and it follows from a little more general results. So suppose that you have a sequence of function fn which converges to f at, let's say, pointwise. Suppose that all the functions are smooth enough that you can take derivatives everywhere. Then we formally compute the difference of the convolution with respect to w dot, and we see that this convolution becomes equal to the difference of the function in 0 times wt, but we can assume that the difference of the function in 0 is 0, plus the convolution between w, and now I don't have any more w dot, so this is a deterministic integral with random coefficient, times f minus fn dot. So by our assumption, if fn dot converges to f dot, we see that the sub converges to 0. And so it is sufficient to prove that if fn converges in 0 and fn dot converges pointwise to fs, and then we can apply Lebesgue-dominated theorem. So for instance, we suppose that the Fn dot are uniformly bounded. Then previous estimate, we can take the limit in n inside, and previous estimate says that the sequence of processes xn converges to the process given by the limit, the convolution with respect to the limit function. So it remains to prove that we can apply this in our case, and we have Fnt, which is given as the limit of the partial sums. Sorry, partial sums. Ft is the limit of partial sums, and we already know that it's given by the Fox-Wright function 0n. We can explicitly compute the derivative in both sides and see that we can bound the function Fn dot by a quantity which is uniformly bounded in 0t, and so we can apply the law of large number to prove that both Fnt converges to Ft, Fn dot t converges to F dot t, and that this function is almost surely bounded in the time interval 0 capital T. And this is enough to prove the theorem. The details are a little bit more complicated, but just a question of computations, nothing more. The last part of the talk, so I should have a few minutes more, is given about the asymptotic behavior of yt. And this is interesting in two directions. The first one is the following. First, we can prove that yt is, since we know that for any fixed time, this is a Gaussian process with given variance that can be computed explicitly. And okay, I will not give you a formula because it's quite complicated, but it doesn't matter. We are interested to see if we have that, to see if there exists a limit law for these processes. And what we see is that actually the answer is yes. There exists a random variable eta that is Gaussian with given with zero mean and given variance, such that yt converges in distribution to eta. And we still require the two assumptions that we said before. So mu should be larger than 1/2 log, and lambda should be larger than 0. And moreover, we can see that this random variable eta is actually a stationary solution of the problem. So if we modify in a usual way the construction by taking, instead of sending the final time to plus infinity, taking the initial time to minus infinity, we can see that y is actually a stationary solution for the problem. And finally, we see that, okay, I just take the last one. We can see not only that I have the Gaussian stationary measure that is invariant for the problem, but that this is also the limit of the empirical means of the processes taken exactly as before. So I take the empirical mean, but now the processes are the integrals from minus infinity to t. Okay, I think that I stop here.
Thank you, Professor, for a very interesting talk. And now, according to the schedule, we have about 4 minutes for the questions. Please answer the questions.
Well, I have a question, if possible. So this your process Y, Volterra process, is it somehow related to the models of anomalous diffusion?
Okay, the answer is I don't know, because it depends on which kind of anomalous diffusion you're thinking about.
Yeah, there are many options. Yeah.
Yeah, exactly. That's the point. I mean, one interesting question in this field is which kind of Volterra equation, which kind of Volterra process you can approximate in this way. And the answer is unknown. At least in the literature, there is no answer about, let's say, the inverse construction. Start with the Volterra process and find a way to approximate it. There is, in my knowledge, there is nothing in this direction. So this should be our next step, to try to invert the construction, going back from the Volterra process to say Ornstein-Uhlenbeck, or I don't know, probably something that will be more complicated, but going in this direction is something that is not done in the literature anywhere. At least I haven't seen anything about this.
Well, I have seen a process which is like fractional Brownian motion with variable Hertz parameter. So it's again a Volterra process where we have this Hertz parameter is now a random variable with gamma distribution. By this your mixture somehow also has gamma, and so people motivate that it is something useful for anomalous diffusion in cells. So probably there is an interplay between your Volterra process and this.
Yeah, probably, yes. As I said, yes, probably.
Yeah, so it will be interesting to see the connection. So thank you.
Thank you.
Once more questions, please. If there are no questions, then now we have break, and in